The Moon is Earth's only natural satellite and its closest neighbor in space. Scientists believe it formed after our planet collided with an object roughly the size of Mars. This catastrophic event occurred billions of years ago. At that time, Earth was a molten mass, and a huge fragment of material was ejected into space. Over time it cooled, took on a spherical shape, and became covered with craters. Today, the Moon orbits Earth, causing ocean tides. Its diameter is slightly more than a quarter of Earth's, which makes it the fifth largest natural satellite in the solar system. The Moon goes through several phases: new moon, full moon, crescent, first quarter, and last quarter. Regardless of the phase, however, it is difficult to confuse it with any other celestial object. It is clearly visible in the night sky and sometimes even during the day. But imagine waking up at night and noticing that the Moon looks unusually bright and large. In a half-asleep state, the change might not seem dramatic, and you fall back asleep without realizing that Mercury has taken its place. The surface of Mercury, the planet closest to the Sun, closely resembles the lunar landscape. It is covered with countless meteorite craters. In size, Mercury is about 2/5 the diameter of Earth, yet it is still slightly larger than the Moon. Because of this, its influence on Earth would be stronger. Nights would become brighter, tides would intensify, and the cycle of phases would be shortened by about 14 hours. Overall, however, such a substitution would not lead to drastic changes. But what if Venus replaced the Moon, the third brightest object in the sky after the Sun and the Moon? Venus is often called Earth's sister planet because their mass and size are nearly identical. From Earth, Venus would appear enormous, about the same size Earth appeared to Apollo astronauts from the Moon's surface. The morning star would shine far brighter than the Moon. Venus reflects 6 times more sunlight and would occupy at least 16 times more area in the sky. Nights on Earth would resemble early twilight. In its yellowish-white clouds, faint swirling patterns could be seen. Most likely Venus would not become Earth's satellite. Instead, the two planets would orbit their common center of mass. At lunar orbital speeds, such a configuration would quickly result in a collision. If Mars took the Moon's place, the difference would be immediately noticeable. Its reddish disk and size twice that of the Moon would be visible even without a telescope. Dark regions on its surface would emphasize its unusual appearance. Even without looking at the sky, people would feel the consequences. Mars is much larger than the Moon, and its presence would disrupt the system's delicate balance. Coastal regions would require urgent evacuation as massive waves, similar to tsunamis, crashed onto the shores. Nights would grow brighter, and Earth's landscapes would take on an eerie reddish tint. On the plus side, telescopes would reveal Olympus Mons, the tallest mountain in the solar system. Over time, Earth and Mars would likely form a double-planet system, making travel to Mars far more realistic. But if we think on an even grander scale and imagine Jupiter replacing the Moon, Earth would cease to exist as an independent planet. It would become a satellite of the gas giant. On one hand, the sky would offer a breathtaking sight. Jupiter's colossal striped sphere would fill the entire horizon with yellow, brown, red, and white clouds swirling through its atmosphere. On the other hand, the planet's immense gravity would trigger devastating earthquakes, volcanic eruptions, and tsunamis. Earth's crust and mantle would be stretched and compressed until the planet was ultimately torn apart, deforming by tens of meters. Unfortunately, Earth's orbital speed is only about 10% of what would be required to remain in orbit around Jupiter. For this reason, our planet would inevitably collide with the gas giant in less than a day. But let us set aside such grim outcomes and imagine something even more spectacular. If Saturn replaced the Moon, the sight would be truly unforgettable. The planet, more than 35 times larger than the Moon, would appear as a vast golden sphere occupying about 18 degrees of the sky. Its famous rings would stretch from horizon to horizon. Earth would orbit slightly farther away than Saturn's major moons, but due to the gas giant's enormous mass, our planet would become one of its satellites. Sadly, Earth's orbital speed would still be insufficient, and within a couple of days it would plunge into Saturn. Before that happened, Earth would have to pass through Saturn's magnificent rings, composed of fragments of comets, asteroids, and shattered moons. This would be an extremely dangerous journey, especially considering that more than 50 moons orbit Saturn. Even if we assumed extraordinary luck and avoided a collision, becoming Saturn's 54th moon would still end badly. The planet's immense gravity would cause global tectonic upheaval, tearing Earth apart until nothing remained. Uranus and Neptune are classified as ice giants. They are roughly similar in size, larger than Earth but smaller than Saturn and Jupiter. Both are covered in ice and display beautiful greenish-blue hues. If either replaced the Moon, the consequences would be similar, so let us arbitrarily choose Neptune. Neptune is about 14 times larger than the Moon and would appear in the sky as a huge bright blue sphere, visible both day and night. It would seem many times larger than the Sun, and solar eclipses would occur regularly. When the Sun disappeared behind Neptune, Earth would be plunged into complete darkness for more than an hour and a half. Neptune's mass is 17 times that of Earth, and its gravitational pull is so strong that our planet would once again become a satellite, this time of an ice giant. Earth's orbit would lie slightly farther out than that of Neptune's largest moon, Triton, and there would be a real risk of collision. Even if we assumed such disasters were avoided, there would still be plenty of problems. Tides would become 1,000 times stronger than lunar tides, and while Neptune's gravity would not tear Earth apart, it would significantly heat its interior. Seismic activity would increase rapidly, triggering frequent earthquakes and volcanic eruptions, and quite possibly, the internet would disappear as well. Now imagine two parallel horizontal lines and connect them in two ways, with a vertical line and with a diagonal one. Which is shorter? Of course, the vertical line is the fastest and most direct path between two levels. By the same logic, it might seem that the easiest way to reach orbit is to go straight up. The lower line represents Earth's surface. Our planet is a complex mixture of countless materials combined into a mass of about 6 sextillion tons, a number with a truly intimidating amount of zeros. Essentially, this entire mass acts like a giant magnet that, among other things, holds Earth's atmosphere in place. The upper line marks the boundary of the atmosphere. Everything above it is orbital space and the open cosmos. However, the atmosphere itself is also made of matter gases with mass and density. When a spacecraft launches, this gas constantly presses against it, creating drag and significantly slowing it down. Flying through a vacuum can be compared to slicing through air, whereas moving through the atmosphere is more like trying to push through thick jelly. Doing so requires enormous amounts of energy, especially when Earth's gravitational pull is taken into account. Airplanes face fewer difficulties because they use air density to their advantage. Engine thrust and wing shape work together. A wing forces the airflow to split into two streams that later rejoin behind it. The air moving over the top of the wing flows faster, and the faster air moves, the lower its density becomes. This is how lift is created. This means that the air flowing beneath the wing is denser than the air above it. That difference generates lift and allows the aircraft to gradually gain altitude. Essentially, wings let an airplane glide through the air. Of course, this would be impossible without a powerful force pushing the aircraft forward. Thrust is required just to lift off the ground, and to generate it, the plane must reach high speed. The required speed depends on the type of aircraft, about 96.5 km/h for light planes, and roughly 241 km/h for a commercial airliner. Just to take off and climb to an altitude of around 3 kilometers, a Boeing 747 burns nearly 3 tons of fuel. That may sound impressive, but let's compare it to a space shuttle. The first thing you notice is its small, short wings, completely useless for a horizontal takeoff. Larger wings would not help either. They are ineffective in the vacuum of space and would be extremely difficult to make strong enough to survive launch. The shuttle's small wings serve only one purpose: safe landing, allowing the vehicle to be reused. Their size is sufficient only to stabilize the shuttle during atmospheric descent and guide it safely to the ground. The engines are not used during landing, and shuttle engines are fundamentally different from aircraft engines. Airplane engines require atmospheric air to operate, while space offers none, so shuttles rely on rocket engines. The principle behind a rocket is easy to understand. Inflate a balloon and let it go. As air rushes out, the balloon moves in the opposite direction. To lift off, a rocket engine must generate immense thrust and burn huge amounts of fuel. In practice, the shuttle cannot rely on its main engines alone. It also requires two solid rocket boosters and a massive external fuel tank, which is jettisoned during the final stage of launch. Reaching orbit demands extraordinary power. The combined thrust of the shuttle's three main engines and two boosters reaches about 3.5 million kilograms of force. To achieve this, the external tank carries roughly 725,000 kilograms of propellant. Controlling such a flight requires engines of astonishing complexity and precision. Could the shuttle be launched by redesigning it to operate like an airplane and using the atmosphere? Unfortunately, no. Maintaining the necessary speed along a diagonal ascent path would require even more fuel. Even after reaching the upper atmosphere, Earth would still not let go. To escape the planet, an object must reach escape velocity, the minimum speed needed to overcome Earth's gravity and enter orbit. For Earth, this speed is about 28,000 kilometers per hour. That is far greater than the speed of sound and many times faster than the cruising speed of a commercial airliner. It is difficult to imagine an airplane flying that fast. The fuel requirements and structural demands would make such technology impractical and astronomically expensive. The realization that space shuttles may eventually become obsolete has driven scientists and engineers to search for better ways to reach orbit and beyond. One futuristic idea is the space elevator, a concept involving a colossal tower extending to a satellite in orbit that moves in sync with Earth's rotation. The structure would need to be about 35,400 kilometers tall and made from an incredibly strong material, such as carbon nanotubes. Elevators inside the tower would be powered by electromagnetic propulsion, and the journey from Earth to orbit would take only about 5 hours. Such a megastructure would make space travel faster and safer, but current carbon nanotubes are not strong enough, so the search for the ideal material continues. A similar concept is proposed by the Space Tram project. It envisions a vertical vacuum tunnel in which a spacecraft would be accelerated using magnetic levitation. With no air resistance, electromagnetic forces would push the vehicle until it exits the tunnel at near escape velocity. Such a spacecraft would be lighter because it would not need to carry large amounts of fuel. However, one crucial question remains unanswered. Could a human body survive such extreme acceleration? If these ideas sound too fantastical, you're right. But there is a more realistic alternative. In the future, airplanes may be used to help reach orbit more precisely, as airborne launch platforms. An airplane itself cannot reach space, but it can serve as a launch base. For this purpose, massive aircraft with wingspans of nearly 122 meters are being developed, capable of climbing above 10 kilometers. A small spacecraft launched from that altitude would not need to pass through the densest layers of the atmosphere, making it easier to overcome Earth's gravity. This approach is already being pursued. Richard Branson is working on it through the Virgin Galactic program, whose goal is to take tourists to the edge of space.